Okay, thank you very much.
Okay, our next speaker is Mr. Lee. He's going to be presenting on the evidence of surface exposed water, ice, in the lunar polar regions, seen by the Moon Mineralogy Mapper.
Thank you, everyone. So today I'm going to present some evidence we found for the surface exposed water ice using MCube data. How can I go to the next slide? Okay, so it has been suggested that water ice may exist in permanent shadow regions of the lunar polar region. Some simulations suggest that we expect more ice on the moon than Mercury. However, the detections of surface exposed ice on the moon are very inconclusive. For example, studies using reflectance spectroscopy either completed by other H-bearing species such as hydroxyl, or the water feature seen by such as aircrust could be either buried ice or surface ice, or it could be contamination. And also the observations from radar is also very contradictory. Epithermal neutron senses only to hydrogen, so it could be OH, H2O, or H. And the on and off band of lemon alpha could be due to both OH and H2O. So we definitely need more direct evidence for surface exposed ice on the moon. And our detection method is quite simple and straightforward. So we are using MCube data in the visible to near infrared band. So in this plot, the black line is the average, the global average spectrum of MCube data OP2C, and the error bar is 2 standard deviation. We can see it has very obvious red slope, and this blue line is the pure ice spectrum in the visible to near infrared region. We observe that it has very obvious opposite trend, blue slope, and also 3 diagnostic absorption features centered near 1.3, 1.5, and then 2. So we just empirically use the 2 threshold. First is the blue slope, and the second, the 3 diagnostic absorption features to detect possible ice features in the lunar polar regions. We don't have to worry about a thermal because this is near the pole, and also we are using thermal using shorter wavelengths because this region MCube data has a highest signal to noise ratio. I want to note that we have to calculate the true reflectance at the shaded region, as we heard from Tom. Ice is not stable at under sunlight, so must be in the shaded region. In this figure, schematically, I'm showing the calculation of the true reflectance at this point, the shaded region, equal to the radiance captured by the sensor divided by the light source scattered into this part. So we're using, because this is a kind of qualitative assessment, so we're using the average MCube spectra in the illuminated region to represent the R0. This is our detection results. The red dots are the possible ice exposures. This is the North Pole, this is South Pole, display from 80 to 90 degrees. The base map is a white mosaic, and the cyan region shows the defined maximum annual temperature, less than 110 K. First, what you get from the map is the distribution is very patchy. So these dots are discrete MCube pixels. And on the South Pole, we see it's quite a discrete, and may have some clusters surround the crater Rozestivinsky, and also Plascate. On the South Pole, we see more exposures, mostly concentrated near the polar region, near the poles, and may classes around create a Hewers, Shoemaker, and maybe this create a called Sverdrup. Now in this plot, I'm showing some spectral examples. This is spectral shows if there is no ice, how the spectrum looks like, and this is a pure ice spectrum. You can do a comparison, and this is 1.3, 1.5, and 2 micron absorption features. And these three plots showing pixels possible to have ice. And we can see they match the pure ice spectrum very well. And then in this slide, I'm showing the average spectrum of all possible ice exposures. And this is North Pole, this is South Pole. So I didn't do any further processing, just put out the MQ spectrum at those exposures. And the right line is the average spectrum, and the shaded region is the standard deviation, 2 sigma. These two figures, the spectra are normalized by its mean value of each pixel, and this is without normalization. This is just a put all M-cube spectra put together, and this is average. And here, for reference, this is pure water ice, and this is what we see in the North Pole and the South Pole. We can see the 3 diagnostic observed features, 1.3, 1.5, and 2, and also the blue slope. Another thing I want to draw your attention is the asymmetric absorption feature near 1.5 also matches with the pure ice absorption feature. So we did a test to want to know whether this is a false positive or something else. So first test, we use a random data set. We use the same mean and standard deviation of M-cube data at shaded regions from 75 to 90 degree. And we generated randomly, generated around 6.5 million points false pixels. And I use the same threshold we use for detecting ice on using M-cube data. And this is the results. So this is a random data set. And this is what we see using M-cube data. So definitely, you cannot reproduce the feature we see on M-cube, use the random data points. And for reference, this is a pure water ice. So does look like anyone. Another test we use is to examine the pixels at shaded regions at a lower latitude, because we know ice cannot be accumulated at a lower latitude. So in this figure, I'm showing the pixels in the shaded region globally. So this is latitude, and this is a density plot. So different color means the number of pixels, and this is a local in-situ angle. So I just cut off at a 90 degree, because if it's above 90 degree means the sun is beneath the horizon, so it's in the shaded region. So we can see even in the equatorial region, we have several pixels in the shaded, in the shadow, and as goes to above 30 degree, you have more pixels. And this is the detection results. So we only see positive detections at latitudes beyond around 70 degree, both north and south. And then we extract the defined temperature and the LOLA albedo at ice exposures. And this is North Pole, this is South Pole, and this line shows the 110K threshold. So mostly is below, most of the exposures are below 110K, but some of them showing several pixels showing temperature around like beyond 110K, but definitely less than 160K. And this is these two plots showing the LOLA albedo. You can see they all above the average LOLA albedo. So LOLA has enhanced signatures. Possible explanations for some pixels showing temperature above 110K. It could be due to map registration, because these are 2 different data sets. So even several pixels offset can give you some temperature difference. And the second one is a different spatial resolution. So M-cube has resolution around 280 meters per pixel. Diviner has 240 meters per pixel. We have to resample it. Or it suggests that these deposits are much younger. So it can be stable. It can be like in the a little bit warmer temperature. All of these are false positive. I talked to Paul Hing. He said some of the lunar surface may have macro echo traps. It's sub-pixel size, so less than the pixel of footprint of diviner. So this could be accumulated at a temperature less than 110 K, but nearby has some region has higher temperature. Then we look at all cube pixels especially at regions with temperature less than 10 K. So this is North Pole, this is South Pole. Essentially, we don't see any ice-like absorption features. You just look at the whole region. So that means the ice exposure is not always associated. Not all low temperature regions has ice exposures. And also we look at the mini-RF data, the CPR map. So the dots, again, the red dots are possible ice exposures, and this is I stretched the mini-RF CPR to highlight the high CPR regions. So essentially, we don't see any clear coherence between the exposure and the mini-RF high CPRs. This may suggest that there are no large blocks of ice, or the ice is thin, or the particle size is small, so it cannot be sensed by radar data. In conclusion, we see possible ice exposures using MCube data, and more exposures in South Pole than the North Pole. In the south, it clustered at the craters Hayward, Shoemaker, and Sverdrup, and mostly associated with temperature less than 10 K, and also show enhanced LOLA albedo. We don't see coherence between exposures and mini-RF high CPRs. They suggest either the ice is thin, or the particle is a fine, very fine particle size mixed with regolith, or this also saying there's no blocky ice. We want to know that because this is relying on the MCube data at a shaded region, so you can imagine it's very hard to get a high quality reflectance data on ALS body in the shaded region. So there could be more ice exposures than we reported here because we don't have data at those regions. And also this study is supporting that the imaging spectrometer can be used to explore shaded region on ALS bodies on other planets. That's it. Thank you, everyone.